Hi, welcome to a new session of Circuits and Networks. In today's class, under one, under transient analysis, we are going to see the response of a source-free RC circuit. So you can see the representation of a source-free RC circuit and the graph of this, which is exponentially decaying in nature. How this is possible? Let us go with the approach. So what is a source-free RC circuit? Suppose a DC source is suddenly disconnected from a given RC circuit as shown below, like this. So initially the supply was connected and then it is disconnected. And due to the initial conditions where the input supply will deliver current to the elements, that is passive elements, capacitor and resistor. So naturally the currents will be developed across these two passive elements. And after the removal of the switch means what, the source it is disconnecting from the passive elements which are connected in parallel. We are in a position to understand that capacitor is charged to a voltage. What is that voltage? So here we are treating the voltage Vc of t equal to 0 as Vc of 0, which is nothing but equal to V naught, assuming that the voltage developed across the capacitor is V naught, and this is our first assumption. Naturally, the energy stored in the capacitor would be half Cv square. So here V is nothing but V naught square. So this we treat as equation 2. And figure 1 is changed to figure 1a. The capacitor is charged and the same circuit it is delivering the current to resistor also. So if we apply KCL at node A, here we are going to get IC plus IR equal to 0, where IC is nothing but C dV by dt plus IR is nothing but V by R will be equivalent to 0. Rearranging this equation, I'm going to get dV by dt plus V by RC equal to 0. Now equation 4 is a first order differential equation. This can be rearranged in the form of dV by V equal to minus dt by RC. So equation 5, uh, you have to integrate on either sides of this equation 5. Then you're going to get ln V, which is equivalent to minus t by RC plus ln A, where A is nothing but the integration constant. So rearranging this equation and framing as equation 6, I'm going to get ln V by A equal to minus t by RC. So this is the equation, and V can be obtained as A e to the power of minus t by RC. In fact, V of t is nothing but the standard equation which we have framed in equation 7. We know that the capacitor was initially charged. Therefore, at t equal to 0, we know that the value of V of 0 is equal to V naught. So if it only we substitute 0 in place of t, then equation 7 it would be A e to the power of minus 0 by RC. In fact, V of 0, which is nothing but V naught from equation 1, is equivalent to A e to the power of minus 0 by RC, which is nothing but equivalent to A. So A is equal to V naught. Substituting this equation in 7, I'm going to get V of t equal to V naught e to the power of minus t by RC. And equation 9 is the main reason, because equation 9 represents the V of t graph, which is exponentially decaying in nature. Just substitute the values of R and C, different values of R and C. You're going to get the different values of time constant. With different times of constants, you can easily plot the graph. Okay, from equation 9, the response of the source-free RC network is exponentially decaying in nature. So when you plot V of t versus t, and if at all you vary the values of R and C, the response due to the initial energy stored and the characteristics of RC circuit, thus it is regarded as a natural response. As T increases, voltage decreases towards 0. So the time constant for RC circuit can be defined as time taken by response to decay to a factor of 1 by E of its initial value. And that time constant, you can see, if at all you substitute the value of e to the power of minus t by tau, if at all the tau value is also equivalent to t, then you're going to get e to the power of minus 1. In fact, that is nothing but v naught v naught by e. That is what we are going to get this equation. So tau is the time constant of this source pre-RC circuit. So its value is nothing but RC. So we have framed the equation of voltage. We can get the value of current, which is nothing but voltage by resistance. So equation 9 and 10, the basic voltage and current representations. We can easily calculate the value of power also, which is nothing but V of t into I of t, which is nothing but V naught square by R e to the power of minus this equation 9 and 10 you can see repeated twice e power, so e power minus 2 t by tau, equation 11. Now energy absorbed by the resistor up to time t is, it would be equivalent to, just you take this equation 11 and integrate from initial condition to t conditions. So this is what we are doing over here. So take the constants outside and integration you apply to e to the power of minus 2 t by tau. So the integration will give you the value here as e to the power of minus 2t by tau. Again, the integral part of the integration, so that is 1 by minus 2 by tau, and the lower limit is 0, upper limit is t. When you substitute the inner values of this particular equation and substituting the upper limit and the lower limit, you are going to get the value of E of t, that is nothing but the energy absorbed by the resistor, which would be equivalent to half C V naught square of 1 minus e to the power of minus 2t by tau. So this is the equation 13. Now if at all you observe carefully, as t tends to infinity in equation 13, from equation 13 it is observed that energy by resistor as 1 by C V naught square. So in fact, equation 4 represents the same equation what we have framed the equation initially for the energy stored in capacitor. So that is nothing but half C V naught squared. So it is clearly understood that the energy which was stored in the capacitor is completely getting dispatched to the resistor. So this is the conclusion of this particular topic. So for a source free RC circuit, we got the time constant as RC. This you remember. And also, when you are going to take the actual conditions for resistors and capacitors, we need to note that to find time constant, resistor is treated as Thevenin's equivalent resistor measured across the terminals of the capacitor, which means we have to take out capacitor from the given circuit and find out the equivalent resistor across it. So how this is done, we'll see with the basic example. In the figure 1 of this particular problem, initially capacitor is charged to 20 volts. Fine. So this is a value of capacitor 0.2 farad and it is charged to 20 volts. Okay. So the capacitor is charged. Calculate voltage across 2 ohms and current flowing through it. Okay. We need to find out the value of current and voltage in 2 ohms with the initial conditions of 20 volts. So how do we solve this problem? So calculating the Thevenin's equivalent resistance first. So as I told you, if at all you need to calculate the resistance, you have to remove this capacitor from the given figure and calculate the R equivalent. So clearly in figure 1a you can see 4 and 2 are in series and they are arranged in parallel to 12. So naturally the R equivalent would be equivalent to A into B by A plus B, that is equivalent to 4 ohms. Once we're done with R equivalent, we can easily calculate the time constant, which is nothing but equivalent to R equivalent into C. C value is given as 0.2 and R equivalent we got the value as 4. So naturally the time constant for the circuit which is shown in figure 1 would be 0.8 second. Good. Now Vc of t is the voltage across the capacitor what it is initially charged with. So it is V naught e to the power of minus t by RC. So V naught, the value it is given as 20. Fine. E to the power of minus t by tau. Tau is RC. The value we have calculated as 0.8 second. So rearranging this equation, I'm going to get 20 e to the power of minus 1.25 t. So this is the value of the voltage of the capacitor. Okay. So that voltage is over here. And we can calculate the resistance voltage because there is a source over here. To the left of this, we are not interested. To the right of this, we are interested because two resistors 4 and 2 are connected in series with the help of formula of voltage division rule. I can get the total voltage, which is nothing but the 20 e to the power of minus 1.25t multiplied with the resistance, that is 2, divided by the sum of these two resistance 4 and 2, which will give you the value of VR of t. So that value is nothing but 6.66 e to the power of minus 1.25 t. I hope you understood this particular solution for calculating VR of t. Once we are done with VR of t, we can easily get IR of t, which is nothing but VR of t by 2. So in fact, this answer would be 3.33 e to the power of minus 1.25 t. So these kind of problems are frequently asked for competitive exams, especially in GATE exams and engineering services exam. So for a practice, you take out this problem. You can see in this figure 2. Initially, capacitor is charged to 30 volts. Okay, calculate the voltage across 6 ohms and current flowing through 8 ohms. So here you need to calculate the voltage and here you need to calculate the current. The answers are given over here. V6 ohms is nothing but 10 e to the power of minus 0.25 t, and current through 8 ohms is nothing but minus 2.5 e to the power of minus 0.25 t. So in the next class, we are going to see the solution. Meanwhile, you try to solve this problem and comment in the chat box whether you are able to solve the problem or not. So I hope you like this video. Please share among your friends. Subscribe to this channel and please press the bell icon for future notifications. Have a good